Hi there, welcome to the session on Kubernetes Fundamentals. This is the first of the videos which we create for a series of videos on Kubernetes, and this video covers the fundamentals, and then we'll slowly move on to the other aspects of Kubernetes which we take session by session, and we gradually move towards understanding Kubernetes in depth. So the coverage will be not just understanding the theory but doing the practical and doing some case studies, how people are using Kubernetes in the industry and so on. So let's see what we have in the agenda for today. So the first of all, we'll discuss what's the problem that lies in container management right now. Like we all know, people are using Docker containers in the industry, but what are the problem areas and how Kubernetes comes in to solve those problems? So that's the first thing we're going to understand, and then we move on to understand a bit more in depth what Kubernetes actually is and what it isn't. It's important to understand what it isn't so that when you are going to deploy Kubernetes for your solutions, you don't make mistakes. So we do that, we understand what it is and what it isn't, and then we move on to the features of Kubernetes, like what Kubernetes has in the plate to offer. So if we understand the features, we'll get to know if it fits right in the use cases in your organization. So that way you'll be able to select if Kubernetes is the correct solution on a given set of scenarios. So that's the third thing. And the fourth thing which we do is we understand, or you can say we discuss a case study where Kubernetes is used in the industry. So that gives an idea like what are the various scenarios where Kubernetes are being used at the moment. And then we move on to discuss a high-level Kubernetes architecture. I say high-level because we are not going in depth in the first session. We are just having a bird's eye view on what the architecture looks like and what are the components around Kubernetes architecture, how they interact with each other and how they work together. So we'll have a high-level understanding of the architecture, and then we discuss some words which we call Kubernetes jargon. Like every technical aspect or any technical thing has its own set of jargons or words which only people who deal with that particular field know of. Similarly, Kubernetes has its share of jargon, so we'll learn about that, so that when we move on to the advanced chapters on Kubernetes, it will be very easy for us to grasp. And finally, we just go through some basic Kubernetes commands as a part of a hands-on demo. We cannot do much on the first session itself because it's imperative to understand various aspects of Kubernetes before you can jump in on and write commands and deploy stuff in Kubernetes. So we'll get to that stage. So we'll just do some basic command line stuff in Kubernetes and see how it goes. So let's move on to the first aspect, that is what is container and how containers are managed today, and what are the problems there in the containers. Alright, so before we move on to Kubernetes, let's forget about it for a while. Let's see what containers actually are. People who have used Docker would have some answers, but let me start from scratch. You might have heard about various applications, software applications written in Java or Python or any other language which are running various set of tasks in the software industry today. Now, take for example, you have a Java application. So the front end is written in Java, and there is a back end. So there are certain functions of the backend softwares, and there are some databases to which these applications connect to. There are some caching layers. So it's a complicated set of a software application that's running. So now this entire set of application is running as a single task. So such kind of applications we call as a monolith application. So a monolith means various modules of the application are connected together. So if something goes down, the entire thing has to go down, or if you have to bring it up, you have to bring the entire thing up together. You cannot uh, take out parts of the application and keep the other half of it running. So that's how a monolithic application behaves. So to get rid of those problems, people started breaking down their applications into smaller services, which are called microservices. So we'll do a session on that as well in the coming days. So just to make the introduction crisp, I must say that when software is broken down into microservices and each service is independent and scalable and does a particular set of tasks, that makes managing them useful. For example, let me give you an example to make things clear. Say you have a website, say a banking website, and you have a username and password, and you log in and then access your account. So what are the various things that are involved here? First, when you open your page, it shows you a front end which has the login screen. So there should be something behind the scenes that is taking care of producing this front end as you can see it. So one application is this user experience application. So there should be some service behind it, some front end service. And then say you put in your username and password. So these credentials are being sent again to some backend service to be checked whether you are an authentic user or not, or whether you should be allowed access. So there should be some identity service behind the scenes that's managing this particular aspect of logging in or not letting the user log in. So if we break it down into microservices, so there should be a identity microservice and there should be a UI based front-end microservice. So now each of these microservice can be hosted in smaller Docker containers. So when you isolate these Docker containers physically or using LXC containers, then these can be independently scaled up. But in order to so there are some advantages as well as disadvantages of using containers. First, let's go on and discuss the advantages. Containers are fast and they do not depend on the platform they are running on. So you don't have to worry where you have deployed, what is the underlying operating system, and so on. So Dockers are useful, like they are portable. You can port your application anywhere, so the developer would not complain any longer that the code is running on his machine and not running on the server. So because the Docker images make things portable, it's the same thing that's running on his laptop as what is running on the server. So it's very reliable, okay, lightweight as well as scalable. But when your application grows and there are lots of microservices and there are huge number of containers running for each microservice, it is difficult to troubleshoot, it is difficult to maintain the scaling or maintain, say you have a huge ingress of traffic suddenly, and you have to scale up your containers from say 20 containers to 100 containers. So it's difficult to manage that thing. For that, various orchestrators came in. One of them is Docker Compose. There is a Mesos Marathon orchestrator, and on the same lines is Kubernetes. We'll come to that. All right. So what are the problems with containers that led to the advent of Kubernetes? Like, why people use Kubernetes suddenly? Why don't they just stick to Dockers? That makes things simpler, right? So what's the problem? Both Linux and Docker containers isolate the application from the host. Okay, before going in, let me just tell a few lines on what Linux containers and what Docker containers are. See, the containers have the same methodology, like they are creating a virtual environment and which are completely isolated, and they allow you to run your application and port them to various environments without any problems. Similarly, there are many container runtime environments. One of them is Docker. There is another called LXC, and there is another one called CryCTL, and so on. There are some of these are proprietary, some of them are open source. So nowadays we have a lot of container runtime environments. So let's just stick to the word container instead of saying a Docker, because that is a proprietary thing belonging to a company that deals in containers nowadays. So coming back, what is the problem with containers? As I was saying, when there is a sudden ingress of traffic and certain situations like this, which makes it difficult to scale up, because a system administrator or DevOps guy cannot just go and run a command to scale up the Docker containers. That is not very practical. Because there cannot be a person who is continuously monitoring something and taking actions based on a certain event that occurs. So it's scalable but not very easy to do that. So that's one problem. Next, what more problems could arise because of this? Because it was not scalable. Containers could not communicate to each other. This is another problem the Docker world faces. Like, say you have 10 containers, and you cannot obviously deploy them on the same physical host. You will have to have multiple physical hosts, and if you don't deploy a overlay network which can talk to each of these containers, because as those who have used Dockers know that every container binds and creates itself a virtual network card with a separate address range, and then communicate with the other containers on the same range. And if you have to allow the external world to access these containers, you have to port forward some port in your external IP which is pointed to another port on the internal IP. Now comes the problem when you have a huge deployment where physical servers are different and different Dockers are running on different physical hosts. So it will be very complicated to manage this port forwarding as well as the entire networking and security. So that's a problem. There are solutions. Like I said, there's a solution of Weave or any other overlay network where you can create a layer of network where the Docker containers attach themselves to, and then they can talk to each other. But again, this creates another layer of management meant for the system admin or the DevOps personals to manage. Not very useful when it is a complicated environment, and which is having huge traffic and managed, not fully automated. So that's a difficult thing to put together. And then containers had to be deployed appropriately. This is a problem. Like, for example, if you have a huge deployment with multiple containers, and say you have to upgrade your version. Say you have this identity service running 20 containers spread across hosts, and say, for example, you have solved this network issue of communicating. Then comes another problem. Say the identity service needs an upgrade. Now you have to update the Docker image on each of those 20 physical hosts. And if you do not have any orchestrator to manage this, you have to manually go in each host and find out what is the current version running, and if at all this service is running on that host or not, and then you have to update the service, I mean the image on each of the hosts, and then you have to restart this Docker containers. So this is a quite hectic thing, and lots of scripts have to be written to manage this, so not at all optimal. The third problem is containers had to be managed carefully. Like if there is an outage and all the 20 containers go down, how do you load balance them? Or how do you bring up a new container? Like if one container goes down, should a new container come in its place? Who would trigger that? So you have to do every of this step, or script every of this step, and manage this all the time using another, say Ansible or any other DevOps tool. So not very appropriate way to do that. Then comes auto scaling. It's not possible to do auto scaling without an orchestrator, because Docker itself is a container runtime environment, or any other container runtime environment just concentrates on how to create the image, on how to run the image, and how it interacts with others. It does not care how much traffic is coming, or whether it has to scale up or scale down based on the traffic. So there is no such mechanism to do that. So that's another vacuum which has to be filled up by something which can intelligently detect the number of requests coming in for a container, and whether the container is able to sustain itself with that number of requests and respond in a given time frame. If not, then bring in more containers. So there should be some logic doing this. Then finally, there's another problem. Distributing traffic was challenging. As I was talking about load balancing some time ago, if there is load and say you have 20 containers already, what is the guarantee that all the requests coming in are equally distributed across those 20 nodes? It doesn't help if you have 20 containers, but the requests are just going to two of them, or one of them, even worse. So there is something that should be able to solve these problems. So what is that? What's missing? The answer is a container orchestrator. So what is a container orchestrator? Before naming that, yeah, the orchestrator is Kubernetes, let's understand what an orchestrator is, and what it does, how it helps. So mostly the orchestrator solves the problems which we discussed in the last slide. So the orchestrator can load balance for you, it can distribute your containers, it can take care of the overlay network, it can make your containers like your services resilient. For example, if a service dies, it can maintain a state. For example, if you have 20 nodes and two of them die, it intelligently decides, okay, now there are 18 nodes, two are missing, so I have to bring up two more nodes to make the entire deployment complete. So there is someone who is watching and maintaining the state for every application. That makes the services more reliable and the user experience better. So that's what a container does in a microservice world. So, as I said, there are many containers, container orchestrators, and one of them is Kubernetes, and it is the most used one, and that's the one we are going to discuss today. So Kubernetes is an open source container management tool. It automates container deployments, scaling, descaling, and load balancing. So let me give you some background on Kubernetes. It is a project which is an offshoot of a Google orchestrator, which Google had been using for many years. That's called Borg, and that project, parts of that project were made open source by Google, so that everyone benefits from it. And there is a foundation called CNCF, which takes care of that, and there are lots of open source contributors as well as some companies which contribute to the development of Kubernetes. So Kubernetes has evolved very well as a container management tool. It is a complete orchestrator, and it performs very well in production environments where there is high load, because it is already battle hardened and tested, because Google had been using this for many years, like another version of this particular tool. And some more facts, it's written in Golang and has a huge community, as I said, backing this. So if you are going to adopt this for your production systems, you rest assured that you will get a lot of support from the open source community as well. Like, it's not that few people are just using it, and if you have a problem, there is no one answering, or you don't get any help online. So that gives a lot of confidence for companies who adopt Kubernetes, and also confidence to technical professionals like us to work on Kubernetes. Like, you're not wasting time learning Kubernetes, because lots of people are using it and it has a huge community backing as well. And it can group n number of containers into one logical unit for managing and deploying them easily. So it makes container deployments easy. So that's just a one-liner that explains what Kubernetes is. So we will be doing various sessions on Kubernetes, understand what are the various things which Kubernetes can do and how to do them, because as technical professionals, it's our job to solve problems. So Kubernetes is just a medium using which we will solve the problems of which various architectures or services are facing. Now, what are the various features of Kubernetes? We'll understand that before we go on to understand what Kubernetes is and isn't. First, you have to know something on the features Kubernetes has. So one is automatic bin packing. I'll come to that. So service discovery and load balancing, storage orchestration, self-healing, batch execution, secret and configuration management, horizontal scaling, automatic rollbacks and rollouts. These are pretty interesting points. So let's discuss each one of them. This is just an introductory session, so I hope you're not getting sleepy because there is no practical yet, but we will be doing some hands-on towards the end of the session. So let's get on in, like what Kubernetes features are. First, automatic bin packing. What does that mean? Kubernetes allows you to pack your binaries and store them as Docker containers and pull the containers from the registry and use them in your deployments. So this entire process can be scripted. Okay, you can write YAML files where you can define which binaries to pack and use for your application, how many replica sets you can create. We will come to these terms later on. So basically, automatic bin packing means it can help you deploy your binaries automatically, and you just write an instruction set and then Kubernetes follows that, and it can deploy things perfectly. Second is it helps us to discover and load balance the services. Now, load balancing is pretty much a term which most of you might have come across. As I said, there is an identity service running 20 nodes, and you do not want your request to end up on just one node. So you want it to be equally distributed towards all nodes. So there are various algorithms which you can define in Kubernetes, and then you can round robin your load across all the containers. So that is load balancing. Now comes service discovery. What's service discovery? For example, you have 2 or 3 types of services and you want one service to be able to talk to another service. So how does that work? Normally, in a monolithic world, we would define the IP address and the port of a service in a config file, and all the other services read that config and then they talk to each other using that hard-coded IP address or port. But it doesn't work that way in the microservices or a container world. Like containers can die and then they can start off in any other server. So in that case, the IP address and the port changes obviously for the services which move into a new server. So how does the discovery work then? Like how do other services discover a service which has just died and moved on to another node, which is very pretty much normal in case of containers. Like containers die and then they are resilient, so they move on to any other node and are deployed again. So how does the other services then discover the new service on a new IP address and a new port possibly? So that is managed by Kubernetes. So it takes care of the deployments that are dying or moving on to other nodes, and then updates the service. There is a service which can discover this and update it to all other services, that now service X is not no longer running in server Y and port Z, and it has moved on to some other place. So that service discovery is managed by the orchestrator, Kubernetes in this case. And then there is a storage orchestration that is managed by Kubernetes. So there are certain services which are stateful or require some data to be stored in a particular disk, which has to be made available to the service all the time. Like you cannot afford to lose that data. So in that case, we use volumes. So we'll come to that, what data volumes are and how they are managed. But Kubernetes can take care of orchestrating these data volumes also. For example, if a identity service needs a particular disk to be attached every time it comes into operation, so Kubernetes ensures that, okay, if identity service is running, I'll provide this disk to be made available to that service. So that is taken care by storage orchestration feature in Kubernetes. Another feature is self-healing. This is like very it sounds like AI, which is the buzzword nowadays. So what is self-healing? Say you have a particular service having a certain number of nodes and few of them get bad. What do I mean by get bad? The nodes no longer respond, or something happened to the underlying server and those containers died. So Kubernetes always maintains state. It can heal itself. Whenever it sees the health check for a particular set of services fail, it tries to relaunch that service in another node, and then as soon as the health checks pass there, it allows the service discovery to let others know that there are new healthy nodes here, and that way it self heals itself. So anything which gets unhealthy is then healed by creating new nodes of that particular service. So that is entirely managed by Kubernetes. And then secret and configuration management. Kubernetes takes care of the configuration of your applications. As I said, you can write your YAML files to manage your configurations as well as manage your secrets. Uh, by secret, I mean your credentials. So Kubernetes takes care of them. And then it can also take care of batch execution. There might be some tasks which you want to schedule and run on a particular time of the day, or you run it on a series with a set of conditions. Say you want a task A to run, and as soon as A finishes, you want to run B and C together. Say this is the situation, and if task A fails, you don't want to run B and C that day. So there might be situations like this in the banking industry or in the media industry and so on. Say you want to send your customers leaflets describing some new marketing campaign or some new feature that has come into your product. So you do not want the mails or the messages to be sent or bombarded to your customers throughout the day. You want it to be sent on a particular time of the day, and if it succeeds, then you want to update some other table in your database or do something related. So these kind of tasks or task loads can be handled by Kubernetes. So that is the batch execution feature in Kubernetes. And then you have another feature called horizontal scaling. This is in times of when there is high traffic or high load in your servers, Kubernetes allows you to automatically scale up your service so that it can accommodate the load. All right, so this is another very good feature of Kubernetes. Like if there is more load and you see the CPU is high, everything else is fine. So just scaling it into two nodes would provide it more compute power, and then the CPU spike would subside. So that's another feature. And then we have automatic rollbacks and rollouts. This is a very important feature in Kubernetes. For example, you have a new version of the application, so you can roll out new feature as a part of rolling updates. For example, if you have 20 nodes and you're not very confident on deploying the new version on the entire 20, you can start a rolling deployment. For example, it will deploy 5 of the nodes and put real-time traffic on it, and you see your logs and know how it's behaving with the new version. If everything is fine and all the health checks are healthy, then it slowly rolls the deployment to newer nodes until all the 20 nodes are updated. And after the rollout is done, if there are some issues that you may be seeing in your application, Kubernetes has feature of rollback, which you can use to roll back to the previous working version. So that's how Kubernetes manages rollbacks and rollouts. Next, we move on to discussing what Kubernetes is and what it isn't. Very important. First thing is, Kubernetes is robust and reliable. It's very robust and reliable. Why I would say that? Because it's resilient. If you write something for Kubernetes, like say, I want my identity service to have 20 nodes, whatever. I mean, I don't want a node less or more than that. Kubernetes follows it to the end. So that is one feature. And then we have another feature in Kubernetes, that it is one of the best solutions for scaling up containers. So when you need to scale up your containers, Kubernetes allows you to scale up. Kubernetes is an orchestration platform. As we discussed, it allows you to orchestrate your containers, and Kubernetes is backed by a huge community. There is a big open source community that manages Kubernetes code, and you get a lot of help from there. So this is what Kubernetes actually is. What it isn't: it is not to be compared to Docker. Kubernetes is not a container management, it's not a container runtime environment. So if you say Kubernetes is not working, It doesn't mean that your container platform is not it's just a platform which orchestrates containers, and if there is a problem with Docker container, it's a problem with the Docker container alone. So it's not to be confused with Docker or any other container runtime environment. It is not to be confused with applications that manage simple architecture. So what it means is, it is not to be confused with Docker Compose. Say someone comes in and says, hey, why don't you use Docker Compose? It's just a single line command which you can use to manage your containers, and you can even scale up and scale down using Docker Compose. So why don't you use that for production? Well, it cannot be compared to Docker Compose. Why? Because Kubernetes does a lot many things which Docker Compose cannot. So it can only be used where you have a production environment, where is heavy workload, and where you have these kind of rolling updates, and you want to manage it in a very professional manner. For things which are less critical, you can use other architectures like Docker, like other orchestrators like Docker Compose and so on. So it's not for simple application architecture, and it's not a tool that you can use for containerizing apps. Mostly managers would say, why don't you break down our monolith software using Kubernetes and containerize it? No, Kubernetes is just an orchestrator that manages containers. It doesn't break down your monolith application into microservice architecture. That's something else for the developers to do, and then you slowly containerize it and run it on a container environment, and when you have to deploy on a production environment, you move into Kubernetes. So that's the difference between what Kubernetes actually is and what it isn't. Now let's discuss a bit on its adoption. This set of figures is from the beginning of 2019, so not very new. So Kubernetes platform had seen more than 4,000 commits. It has a growth of 25% unique contributors to the projects. It's in the top of 0.01% of all GitHub projects, and 3,500 plus external projects are based on Kubernetes. So that says, speaks a lot on how much Kubernetes is being used throughout the industry, and so it's really worthwhile to learn Kubernetes. And since I said these figures are more than 6 months old, so things would have moved east after that. So things have moved towards the better. So these are some companies which are currently using Kubernetes. Some of the big names are here. Huawei uses it, Microsoft uses it, Weaveworks, CoreOS, Red Hat, and so on. These some of these are contributing to the Kubernetes projects, and these are the companies that use Kubernetes, DigitalOcean, OpenAI, big projects. And even there are some applications which are completely oriented, Kubernetes oriented, and it's really going good, and is a very resilient orchestrator. All right, so this is just a overview on how Goldman Sachs uses Kubernetes to solve its problems. They have more than 1 million traffic at all times. Like you will see, it's hovering around a million all the time, and this is between January to June 2019. And due to this, for sustaining a million traffic all the time in their mobile apps and on the desktop portal, they were facing a lot of problems with their monolithic application written in Java. So they started breaking it down into Docker containers, and they then were looking for a solution to deploy it, and they eventually deployed it on Kubernetes. So they have their client data, vendor data, market data, and unique data. All of these go through a set of analytic engines, and they do all sort of analysis of the data. Like this is a stock marketing application, so they measure the performance, the risk, and the tailor solutions for their clients, and the clients use the Goldman Sachs application on their Android mobiles or iPhones or in the portal, and use their APIs to access this data, and based on that they do their share trading on the share trading market. So this application faces a lot of ingress of traffic, and it has to do a lot of analysis because each person or each shareholder who is using this application might have his own data set. So all the calculations are done in the backend. So all these services have to be quickly scalable, quickly being deployed, because this is a finance application, so there is no room for error. So Kubernetes has been a very good orchestrator for them, and they have seen a surge in traffic since they have been using it from the last year, and there has been a good user experience. So if a company as critical as Goldman Sachs, which is depending on their technology to drive them forward, so if they can use Kubernetes, then it proves like this is one of the best. And if you go through other case studies of Kubernetes, you will see lots of games like Pokemon Go, and there's a game called Angry Bird which went viral. So these kind of viral games need a lot of backing in terms of supporting their microservices, and Kubernetes has been used in them as well. So anything goes viral, you do not know how you will scale it up, and it needs to be scaled up from uh, say 10 to 100 to thousands in a matter of few seconds. So Kubernetes has stood up the test of the times, and it has done really well as an orchestrator. So let's discuss a bit on the architecture. As I said earlier, this is a very high level architecture, so you would not get into the details of each and every component, because those are some are the aspects which we'll be discussing one at a time in separate sessions, because we are going to create this Kubernetes course in depth. So you will be discussing each and every aspect as a part of a separate session, so that the understanding would be very good and you can implement it in your organization or anywhere you want with full confidence. So coming to this diagram, let's start from the left and move towards the right. Okay, so there's the UI and the CLI. All right, there's a UI here, which is a graphical user interface for Kubernetes, and there is a command line interface for Kubernetes. So if you want to interact with Kubernetes, you can use a Kubernetes dashboard, which is having a UI, and you can use some command line options as well. And using this, we trigger some APIs of Kubernetes. Like Kubernetes itself exposes some REST APIs which we can trigger to send in our requests to the Kubernetes cluster and do what we want it to do. Okay, and then this API sends its request to some exposed ports in a master server. So the Kubernetes cluster normally comprises of a master server and some slave servers. Okay, The master server takes care of that API request that is coming in from the one who is running the cluster. And it also keeps an eye on all the slave nodes and whether they're healthy and ready for taking in the task loads. So whatever tasks we will deploy, for example, you deploy that service which is spanning across 20 containers. So the master will take in the request and it will deploy the service on the available slave servers. Okay, the master further contains some components. One of them is the API server, which is where the API requests would land in. Like as I said, it exposes some REST APIs which the controller means you and me who are running the Kubernetes show can request Kubernetes on that API. And then there is the scheduler. The scheduler takes in the requests and schedules the tasks on the nodes or the slaves. And there is a controller which takes care of all the signals coming in from the nodes, like what is going on in node number 2, what is going on in node number n. So it takes in those signals, processes it, and takes actions based on that. And there is a key value store called etcd, which Kubernetes uses to maintain state. Okay, so maintaining state means for example, we have commanded Kubernetes that you have to maintain 20 containers of our identity application. I'm reiterating the same example so that we stay in perspective. So now what the master server does is it maintains that state and keeps the record in the key value store. Like if it is identity, maintain 20 healthy containers. So the controller takes that request and sends it to the nodes and ensures that 20 of them are spread across these 3 slave nodes which are in operation. Okay, and if one of them goes unhealthy, it takes care to deploy that missing service in some other node so that the count always stays at 20. So this is what the master does, and the slaves just host the containers over them, and they have a slave component in them which continuously talks to the master controller and tells about the state of the services running on it. And for connecting, the master also is connected to all the slave nodes using an overlay network so that all the containers can communicate with each other and with the external world. And also the slaves are connected to a container registry from where the container images are pulled. So that is another pipeline which would be operating and pushing the container registry with the newer versions of images and so on. So that is something we'll discuss in depth later on. And for the external world to access these containers, they go in through some load balancers which are in a DMZ, demilitarized zone, for security, and these port forwarded to the internal IPs and ports where the containers are actually running the services. So the external app would never know what is the internal IP and port where that service is running. So that way the services are safe. It would only know the IP and the port of the load balancer from where it gets the response. So that's how it is at the moment, the architecture. So the external network, and then comes the DMZ. DMZ knows which internal node to connect to for the external request, and this is the internal network. All right, apart from that, we have certain things like storage services, monitoring, log aggregation, and analytics. So there are some internal services for Kubernetes which manage these roles. So we'll come to all these aspects in future sessions, as I promised. Now we'll discuss some jargon which we use in the Kubernetes world. Okay, so as we discussed earlier, in Kubernetes, when we deploy a particular service, we call it the deployment. So the deployment comprises of the number of instances of the service which we deploy. For example, if there is a deployment which we call my deployment, and there are 4 replicas, that means there would be 4 copies of this service running. Okay, now these services run on various slave nodes, and each slave node has its own internal IP, and we can run one or more services on a particular node, and each of these instances of services are called pods. Okay, so here is some terminologies which you will come across now and again in the coming sessions. And first one is control plane. The container orchestration layer exposes the API and interfaces to define, deploy, and manage the lifecycle of containers. So what is the control plane? Kubernetes master server has a controller. You might have heard about that some time ago. So this controller comprises of various components which make up the control plane. So the control plane is the one where the one who is running the Kubernetes cluster and providing the workload uh, communicates to. Okay, so control plane exposes the API and the interfaces to define, deploy, and manage the life cycle of the containers. So it is the interface or the REST API or the dashboard which you use to communicate to the cluster. It does not care about what data or what container you have deployed within. So that comes on another layer which is known as the data plane. So data plane takes care of the container image you are going to use, how much CPU would be provided to that container, how much memory, network, and storage that containers can use. But the control plane takes care of the entire orchestrator, like what are the master servers, what are the slave servers, and what are the APIs which are exposed, and where you can provide your requests for your tasks to be deployed. So that is the control and the data plane. Then comes the controller. The controller is a control loop that watches the shared state of the container cluster through the API server and makes changes attempting to move the current state towards the desired state. So the controller takes care of maintaining the resiliency of your Kubernetes cluster. Cluster. Cluster refers to a set of machines called nodes that run containerized applications managed by Kubernetes. So what happens here is when there's a cluster, it takes care of the master node and the worker node and all the containerized applications. So the entire thing is known as a cluster. And then comes the daemon set. Daemon set ensures a copy of a pod is running across the set of nodes in a cluster. So uh, it's just a file where we define uh, that each copy of pod should run on all the nodes. So you can set your constraint there. Alright, these might seem a bit vague at the moment, but when we this is just for your record, just to keep everything in perspective. Like, these are the terms which will come in later on in the future sessions, but when you really do them one at a time, it will be more clear. So just go through it now, because you'll be hearing about them later on. Deployment: an API object that manages a replicated application. Okay, uh, this is something which you won't understand at the moment, but we'll discuss it later. But a deployment, you can say in layman's terms, is a set of various services which, when deployed together, lets you achieve a certain task. For example, if I want to deploy my banking application, I will require that UI microservice and that identity microservice for logging in. So my deployment file would comprise of these two microservice images, how many of them have to be deployed, and what is the health check for each one of them to call them healthy. So the entire thing can be grouped under a logical name called a deployment. The node is a slave of a Kubernetes. Like in a Kubernetes, I said there could be one or more masters, and then all the slaves are attached to the master. So each of these slaves is called as a node or a worker. Then comes the pod. As we were seeing in the previous diagram, the pod is the smallest and simplest Kubernetes object. Pod represents a set of running containers on your cluster. So this one, say you have some containers in your cluster. Say for identity, I have those identity containers, so all of them do the same task, so I can group them into a pod, right? Then comes a service is the abstract way to expose an application running on pods. For example, let me go back to the diagram. Say you have this identity pod, and say this pod 2 is also an identity pod, but they do the same task, and you want to expose them to the external world as one port and IP. Okay, so that can be done using another abstract layer called a service. So the service will logically define what pods are running behind it and doing a similar kind of a task. Then comes the volume. This is pretty simple. Volume is a directory containing data which can be made accessible to containers in a pod. And workloads are objects which you use to manage and run your containers on the cluster. So these are the terms which will come later, and you will understand them better when you come across them. Label, these are also some nitty gritties, you can say. Like there are certain complex situations when you are running multiple pods and you have to identify each pod, and there you use these kind of attributes and label them. So these are those jargon. The main things to remember, the takeaways are control plane, data plane, what they are, and cluster, obviously what it is, pod, node, volumes. Okay, and from this slide, namespace, yeah, it is an abstraction. Like in Kubernetes, you can again define namespaces. For example, you have your office, and you have in deployment, and you have various departments in your office. One is the billing department, and one is the ETL department, where they do the data science and deductions, and there is a front end where they take care of the UI, and there is another department which manages the back end or the databases. Now each of these departments have their own deployments and microservices, and you want to logically separate them in Kubernetes, but you have the same Kubernetes server. But you don't want the guys in the billing department to see or tinker the microservices belonging to the back end or the front end department. So how do you abstract that? So you can use namespaces. People accessing a certain namespace can be authorized to or to not be able to see the deployments in other namespaces. So it's just a mechanism to support multiple virtual clusters on the same physical cluster. And then comes extensions. These are software components that extend and deeply integrate with Kubernetes to support new types of hardware. All right, for example, there is a new hardware which is not supported by Kubernetes. You can use extensions which can allow them to integrate it with Kubernetes. Image, this is a stored image of a container. Job is a finite batch task. As I said, Kubernetes has the capability to run tasks as batch jobs. So that's the job. And then kubectl. This is a command line tool for communicating with Kubernetes API server. Okay, so we have two options for communicating with Kubernetes: kubectl and using the dashboard. So kubectl is the command line option. Kubelet, an agent that runs on each node in the cluster. This is the agent which runs on each slave node, and it updates the master on the state of the slave. And then the API, we have discussed this. Kubernetes exposes some REST APIs for you to be able to provide Kubernetes task loads. And then Kube API server component on the master that exposes the API. So this is related to this. And then Kubernetes controller manager, the component on the master that runs the controllers, and kubeproxy that allows you to proxify the request from the external world to the internal IPs and ports of the running containers. So these are pretty much the basic terminologies which we use in Kubernetes. Just ignore if you don't understand some things, because these will be repeated again in the future sessions when we do some in-depth learning on this. Now it's time for a bit of a hands-on. It's very basic today, so we'll just use some kubectl commands to do our hands-on. This is the first session, so we don't have much to do here. So I have installed Kubernetes already, and this is the master node to which I have logged in. So today I'll show you some simple kubectl commands and how it can interact with the Kubernetes API, and later on we learn how to install this and how we can access the Kubernetes server using the dashboard as well and things like that. So this is how we invoke the command kubectl. If I don't give any options to it, then it will just print what I can do with this command. Okay, so this is the help page which comes in. Now if I want to see the version of Kubernetes running here, I just write kubectl version, and it says the client version. That means this kubectl client version is this, and the server version is this. Okay, so I am running a pretty much updated version of Kubernetes. I am using a stripped down version of Kubernetes called K8S. We'll come to all those things later. There are multiple ways to install Kubernetes as well, so we'll get to all these things later on. Okay, so next is how to get a state of the cluster. Kubectl get nodes. This tells me if I have a master and how many slaves I'm having. So right now I just have a master server which is running on this particular IP. So it just shows that there is this IP and this is the master. I don't have any slaves. So I use this master as a master slave. Like this same server is the master and the same server is the slave. But in a production scenario, we'll have multiple of them. So when we do our installation in forthcoming sessions, we will obviously do in a multi-node cluster. So this is just a single node cluster with one master. Okay, and it has been running for 5 days and 5 hours, and this is the version and so on. So if we had slaves, it would list all the slaves as well. Now there is another command which can show if there are any pods which are running. I have actually run one of the pods, so which is just an example Tomcat deployment, so it shows that this is running. Now we'll go in depth in the future sessions, as I promised. Like this is just a demo, like what are the various commands and how it is answering our commands. So get pods gives us this, and say I want to see pods for various namespaces. This is just for the default namespace in which I am logged into. Kubernetes has its own namespace as well and runs certain commands, certain services on those namespaces. So alright, I made a mistake there. It should be all namespaces. Okay, so it shows all the pods that are running in various namespaces. This is obviously our deployment, which is running in the default namespace. This is the system pods which are run by Kubernetes itself. So this is the DNS service pod, this is the Helm, which is the version management, this is traffic, and this one is as well as traffic. These are the proxies. So we'll discuss all this. So it shows like if all of them are running or not, what's the state, and whether they are getting restarted and stuff like that. So these are some of the basic commands here. So what's next? We'll be learning different ways of installing Kubernetes. As I said, Kubernetes can be installed in many ways. It depends upon the scenario and the premise. For example, if you're a developer who wants to install Kubernetes and try it out on the laptop, then there's a way to do it. And if you're doing it for a production system, it's a different way to do it. If you're doing on a stripped down system or a Raspberry Pi, there's a different way and a different flavor to install over there. And there is no easy or difficult way. There are different methods of doing it. You can even use tools like Ansible or Puppet manifest to install Kubernetes. We'll discuss various types of methods which are used in production scale for installing Kubernetes as a part of a different session. And then we'll do a deep dive into the Kubernetes architecture, as we just did a high level discussion on the Kubernetes architecture. We'll just go a bit more deeper into each and every component and how they interact with each other and how we can interact with those components and put in our commands and make the Kubernetes cluster behave in a way we want it to. So we'll do that. And another thing which we are going to do is we will be writing YAML files which would allow us to deploy various applications in Kubernetes. So we'll understand how these files are written and how we can set up instruction sets for Kubernetes cluster to do the deployments. We'll also probe the Kubernetes dashboard, how to install it and how we can use the dashboard to do our provisioning if command line is not the way to go for you. However, you should know the command line as well, because when you're automating something or writing scripts, command line should be the way to do that. And then we move on to logging and troubleshooting, where we will see how we can solve problems if there are any when Kubernetes is running in a production system, and how to detect the issue from a log and how to troubleshoot that. And then we'll also do some advanced Kubernetes concepts which will help you to go very deep into this orchestrator and allow you to be confident and deploy it on a production premise. And finally we'll do some case studies where we'll know how people are using Kubernetes in depth, and we'll see what challenges they are facing and how they are solving them. So we'll have lots of sessions on Kubernetes, and we'll learn a lot to master this particular orchestrator, because this is going to have a great future in the orchestration and the containerization industry. And because more and more companies are moving towards microservices, it is imperative that we learn Kubernetes and how we can deploy Kubernetes on cloud. Apart from the local installation of Kubernetes, there are some cloud providers like AWS who provide their versions of Kubernetes. For example, as I said, AWS provides EKS, Elastic Kubernetes Service, and we have Google Cloud, which provides GKE, the Google Kubernetes Engine. So all these go a long way to take or leverage Kubernetes as the next best orchestrator. So it's going to be very exciting learning this and putting various Kubernetes skills into practice. So stay tuned. Have a good day.